17.1 Mechanical energy. Physics is the study of energy, but energy is quite an abstract concept. It's hard to define. So instead of defining it right off the bat, I'm going to explain it using an analogy. Energy is a lot like money. Since money is something you pretty much understand, let's look at some of the properties of money that can be compared. Money can be stored. If you have a savings account, you can put a certain amount of money in the savings account and it will be stored up for later use there. However, you can also have money available to use if you have a checking account or if you carry cash. Unlike a lot of things we talk about in physics, money has no direction. You can't really talk about having $5 to the left. No, you just have $5 or you don't. And so negatives and positives in money refer to loss and gain. Negative money is a loss. Positive money refers to a gain of money, not directions. Money can be converted to different currencies. You can take Canadian dollars and convert them to euros, for example. And perhaps the most common property of money is that money can be used to buy stuff. In fact, if somebody asks you to define what is money, it's kind of a hard thing to define. But probably the best definition that you could come up with is money is used to buy stuff, or it's the ability to buy stuff. It's not a complete definition of money, but it's a reasonably good one. We're going to take all these properties of money and look at them in terms of energy. Energy has a lot of the same properties. Energy can be stored. In this case, it's stored in the form of potential energy. Energy is also available to be used or visible when it's in kinetic form. Energy has no direction. You don't have energy to the left or energy to the right. Energy is a scalar, so it doesn't matter which direction it's in. Energy can be converted from one form to another. And energy can be used to do what we call work. Work is a word in physics that just refers to the transfer of force from one object to another. So energy can be used to transfer force. The best definition that is given for energy has to do with this ability to do work. It's not a very complete definition of energy in that it doesn't say all that energy is, but it's the best one we have because energy can be quite an abstract concept. There are many different forms of energy. You may have studied these forms of energy in other courses. In fact, all the different branches of physics are really different studies of the different types of energy: light energy, sound energy, electrical energy, chemical, magnetic, mechanical, heat, or elastic. Physics 20 and most introductory physics courses is mainly the study of mechanical energy. If you go on and take Physics 30, you'll study light energy, electrical energy, and magnetic. Mechanical energy is the energy of moving objects. So mechanical energy has a lot to do with Newton's laws, which you've already been studying, as well as speed, velocity, and acceleration. All forms of energy can be described in terms of two main categories. These are not forms of energy themselves, they're actually just categories to describe the forms of energy. The first category is kinetic energy. Kinetic energy has to do with the motion of an object. It's the energy of movement. Kinetic energy is the energy due to the movement of an object. And it has to do directly with the speed of the object. In fact, the formula for kinetic energy has speed in it. The second category of energy is potential energy. This is energy that sits and stored in an object, even if it's not moving, available to be converted into kinetic energy later. Potential energy is the stored energy of an object due to the object's position or location. For example, an object that's located at a very high height has the potential to fall under the force of gravity and gain kinetic energy. So height is considered to be a type of location for potential energy. All forms of energy are scalar quantities. What this means is that there is no direction associated with energy ever, and even better, you can just directly add energy to energy without having to worry about vector addition or angles. Energy is a lot easier to do calculations with. Energy is measured with the unit joules. The symbol for energy, no matter what type you're working with, is an E, and the unit is always the joule no matter what form of energy you're working with. Now let's look specifically at mechanical energy. Mechanical energy is equal to the kinetic energy of an object plus the potential energy of the object. Kinetic energy is given by the formula Ek equals 1/2 mv squared, where Ek is the kinetic energy, and that's a little subscript k next to the E indicating kinetic. This is measured in joules. M is the mass of the object that has kinetic energy measured in kilograms, and v is the speed of the object in meters per second. Potential energy has the formula EP equals mgh, where EP is potential energy, E subscript P, the P indicating potential, measured in joules. M is the mass measured in kilograms. G is 9.81 meters per second squared, the acceleration due to gravity on Earth. And h is the height of the object. How high it is up changes how much potential it has, and this is given in meters. It's important to note that this formula for potential energy only applies when we're talking about gravitational potential energy, the potential energy due to the height of an object in a gravitational field. There are other forms of potential energy with other formulas, but we're not going to look at those here. Let's look at an example. A 0.50 kilogram ball is falling at 10 meters per second when it is 30 meters from the ground. What is the ball's mechanical energy? We start by calculating the two forms of energy it has. Kinetic energy is 1/2 mv squared, which is 1/2 0.50 times its speed, 10 meters per second squared. This gives us a kinetic energy of 25 joules. The potential energy of the ball is mgh. This is 0.50 kilograms times 9.81 meters per second squared times the 30 meters of height that it has. This is 147.15 joules of potential energy. The total mechanical energy is Ek plus Ep. So it's the 25 joules plus 147.15 joules is 172.15 joules, and in correct significant digits, this is 1.7 times 10 to the 2 joules. Another example, this time solving for something inside the mechanical energy formula. A roller coaster car carries 2,000 kilograms of mass. How fast is it going when it is 25 meters from the ground? If it has 9.5 times 10 to the 6 joules of mechanical energy. The mechanical energy is 9.5 times 10 to the 6 joules, and it's the potential energy plus the kinetic energy of the roller coaster car. The potential energy is mgh, which is 2,000 times 9.81 times 25 meters. This is a potential energy of 490,500 joules. So the mechanical energy is 490,500 joules plus kinetic energy, which means the kinetic energy can be solved for by subtracting potential from mechanical, and it's 900,950 joules. Once you have the kinetic energy, you can rearrange the kinetic energy formula to find the speed. Ek is 1/2 mv squared. This means that v is 2 Ek divided by mass square root. So the speed is 2 times 900,950 joules divided by 2,000 kilograms square rooted, which is 95 meters per second. Before we finish, we need to make a quick note about the joule. The joule is a metric unit in that you can put prefixes on it like kilojoules and centijoules and decijoules, but the joule is actually just a constructed unit. It's made from the base units, meters, seconds, and kilograms. Let's look at the kinetic and potential energy formulas to see how they could be constructed from these units. Mass is in kilograms, and speed is meters per second, and speed is squared. This is a kilogram meter per second, meter squared per second squared. Potential energy is mgh. This is kilograms times meters per second squared times meters, which is the kilogram meters squared per second squared. All these base units combine to form the actual unit of the joule. 1 joule is actually a kilogram meter squared per second squared, but this is too difficult to write, so we usually just write it as a joule.